All right, welcome to the final lecture of the class. Time goes by really quickly. Um, so the plan for today is I want to finish this uh, module, and this module will be part of your quiz. And then whatever time we have left, we're going to talk about other stuff. Those stuff's not going to be in your quiz. Okay? So a lot of things to cover, so I'm going to go rather quickly. So last thing we were talking about was how do we fix the synchronization issue, and then how we kind of reason about different timings, as well as how do we make sure that even if the cores and the processor are reordering instructions, we still maintain some form of a correctness, some form of an ordering for the system. And that was the motivation behind this synchronization primitives that I said could be implemented both in software and in hardware. Hardware actually has a big role in synchronization primitives. We talked about two ways of synchronization, the consumer producer and the mutual exclusiveness. And the first thing that we presented was the fence instruction, which what it does is that ensures that things are serialized at the point of the fence. We particularly talk about RISC-V because that's what we do in this class. RISC-V has this instruction called fence.i, which what it does is basically serialize everything at that point. We also talked about additional capabilities in RISC-V architectures, which what it does is allows you to pick which type of orderings do you want to enforce. For example, you can order read reads, you can order read writes, you can order both reads and writes, and so on and so forth. So essentially, you can pick which one of these orderings has to be enforced for your code to work properly. The idea then would be that you have this support in hardware. The programmer basically takes this and put it in their code and ensure that things, even if they are being reordered, can still, produce the correct results. In addition to fences, there are other primitives that are very important. The ones that you probably have some background on it when you take in some course in operating system is semaphores, or people also sometimes call them barriers. What this does is essentially it synchronizes all the cores at the particular point. So it's not about a particular load or store. It actually creates some form of a barrier, some form of a physical barrier, which what it does is that if I have multiple cores, okay, so one core, another core, another core, I can have many, many cores. What this barrier does is that literally like an instruction or an API that basically says the following, that cores cannot continue unless all the other cores reach to this barrier, okay? So essentially, we are guaranteed that when I'm executing this point, all the other cores have reached to this barrier. Which one go first, we don't know. Again, it would be a synchronization problem, but at least we know for sure that it's not possible for this, for example, processor to continue executing instructions unless all of these following processors have reached to this barrier, okay? We can implement this in software, we can implement this in hardware. So it kind of like looks something like, for example, for the code that we had in the past, if I put kind of like the barriers here, and again, what exactly is the syntax depends on the operating system that you have or the ISA that you have. But for example, if I put some form of a barrier here, let's say call it barrier like B function B1, and I put B1 here, what this means is that it's guaranteed that these two instructions will finish before these two instructions execute, okay? Because essentially what it does is that at this point and this point, these two processor has to be at that point. So that's kind of like, ensuring the time synchronization between the cores. This is very useful when you have this kind of a producer-consumer model specifically, where you want to, for example, say that, okay, I want to produce the results here and I want to consume it here. So that's how I put the barriers this way, okay? How do we implement it? In hardware, usually it's implemented as either a hardware OR. A hardware OR, you can think about it as like, a giant OR gate that basically what it does is like when all of these becomes when only becomes one when all of these guys become one, okay? Or it could be as a one hot encoding. So think about it as a register, which we have a bit for each of the processors. So let's say if I have like 5 different CPUs, initially all of them are zeros. When they reach to the barrier, they flip the bits to one. And this will only continue if all the bits are one. So this is also how we implement this in hardware as well, okay? Any questions here? Yes. Uh yeah, so a hardware OR is this weird thing. So it's actually has a meaning in hardware, which means that if all the lines become one, like it's literally a wire that you kind of like combine them. So in order for this to become one, all of these should become one. So think about like a little charges that you add together. So that if it's larger than some threshold, it just jumps up. So that's how it is. Yeah. Yes, fences are usually implemented as local, and then barriers are mostly global. But just keep in mind that fences has a specific meaning. It's just serializing load and source versus barriers is essentially a time synchronization primitive. So it's actually, even if, for example, you have an ad, you cannot run that ad before the others reach that point. Um, Fences can also be implemented cross-core. So, I mean, usually we assume it's local, but there are actually implementations that allows a global orderings of memories. All right, so that's it with fences and barriers for kind of like a more of a producer consumer. But as I said, we also have the mutual exclusiveness as another form of synchronization, and that's actually very common and very popular. So the idea of mutual exclusiveness is that you can technically kind of like let things be reordered or unsynchronized as much as they want. But then there is a critical section. There is a section that you really care about. There is like a one variable or sequence of variables that you're really worried about. And what you do is that you put that into this sort of mutual exclusiveness region, which only and only one of these cores can write at that point. So you sort of kind of guarantee this, that if someone is trying to like read and write to that section, all the other ones cannot access that, read that, write that, and then doing anything with that region of the code, okay? So this is usually implemented as some form of a lock, okay? So the idea is that you kind of put your code into this code segment that is usually start with what we call an acquire instruction, and then ends with what we call a release instruction, okay? And then the lock is essentially a variable. Think about it as like, a flag, 0 or 1. And the mutual exclusiveness is basically this thing that's saying that only one of these cores can acquire the lock. So the entire correctness and the entire fundamental part of a lock is only one of the cores can acquire the lock. If multiple cores can acquire the lock, so you're back to the square one. You have the same problem that you had before. So you have to implement this acquire and release such that if multiple cores wants to grab it at the same time, you are guaranteed that only one of them can grab it. How do you kind of decide which one to grab? It's typically based on random behavior. It's based on arbitration. It's kind of like a first come, first serve. There are lots of works on kind of thinking about the fairness of the locks and all that as well, which is kind of beyond the scope of this course. But generally, if multiple cores trying to grab a lock, you give you give it to only one of them, and that one could be just a random selection. Okay. So in this case, for example, you don't know which one though. So this important things about mutual exclusiveness is that it doesn't enforce the ordering per se. What it does enforce is it enforces that either this runs this in entirety run first, or this one in entirety run first. So it could be like 1, 2, or it could be 1, 2. Okay. But it's not possible to kind of like run this one and then this one and then this one and then this one. Things like this cannot happen. So you run the entire lock in entirety, and once you release it, then the other one can grab the lock and run it. Okay? This actually brings a very important concept in consistency called release consistency. So actually, RISC-V and many other ISAs support release consistency, and that's kind of like one of the most popular ways of implementing a memory model. So the idea of release consistency is the following, is that I don't care anything before acquiring the lock or anything after acquiring the lock. You can reorder things as much as you like. What I do enforce, and when I say I mean the hardware, is that it guarantees that once the lock is released, all the writes within the lock section has been observed by all the other cores. So essentially, we serialize all the reads and writes within the lock from the outside. Usually, also based on the memory model within the lock itself, things are serialized. So typically you can assume that there's some form of a sequential consistency going on within the lock itself, although that's kind of like depends on the exact implementation. Sometimes you're allowed to do things, you can or reorder things within the lock itself. But most of the time, the most common implementation is that if I have a bunch of load and stores, and then have the acquire instruction, and then bunch of load and stores here, and then have the release instruction, and then bunch of load and stores here. Well, what happened is that I can reorder these things as much as I want. So there is no reinforcement of read reads or write reads or read writes or write writes. So none of them is being enforced here. Same for here. But what it does enforce is that it usually enforces the entirety of this thing here. So all of this is being enforced. And not only that, we also at this point, we are guaranteed that all of these reads and writes are being observed. So at this point, we are guaranteed that everything here within the acquire lock has been executed. The nice thing about this is that you can then leave everything else alone. So you can let the processor to reorder as much as he likes in other part of the core. You just have to be careful about the parts that you're really worried about reordering, right? So your random stuff can just go outside the acquire and release, and the core can just optimize the performance as much as it wants. But then in that kind of like section, you say that don't touch this code, right? So don't reorder it, don't do any sort of optimization here. That's the part that I want. And of course, as a designer, you want to minimize that, right? Because the more you put things inside that acquire release code section, the slower your system will be. So you want to minimize that, but then the nice thing is that you can like have a full understanding of what exactly happening during that code section in your code. Okay. So how do we actually implement this? Yeah, bunch of questions. Yeah, go ahead. Why do you want to mutex for read? Yeah, you can mutex for all of them, right? So for example, sometimes you have these read that you want to enforce, right? So for example, if I have like something like if flag is equal to 1, and then like have like a is equal to address like A0 or something. If I don't enforce the read reads, these things can also be reordered in some sense, right? So you have to be careful about the reads as well. Yeah.
So outside of the lock, when you say that none of the memory orderings are enforced, should it depend on what the memory order is?
Yeah. So that's what I'm saying, that it depends on so the question is like which one of these are enforced wouldn't be dependent on the memory model. Yes. As I said, usually when we say release consistency, we mean that the memory model is based on release consistency. It's that like the most relaxed version. That is, you're allowing everything to be reordered. Okay, so that's your memory model. Okay, how do we implement the release and acquire? Because the important thing is that this thing has to be implemented such that if multiple cores trying to run the same code, only one of them should be successful, right? So the acquire itself is a function, right? So for example, let's say I implement the acquire function, something like this. So it's a function, and the way it works is that it should only return 1, which is lock equal to 1, to one of the cores and not the other core. Okay, so let's see how we are implementing this in real world. Let's say that my function is something like this. Typically, lock is implemented as a spinning busy wait. So it takes the lock as an input, okay? And what it does is that it's spinning on the lock. So it's kind of waits until lock becomes 1. If lock is 0, it just stays in this while loop. Okay, so lock is like implementation of lock is very important to be efficient, because essentially what it does is it's some form of like it stalls the processor, right? So the processor kind of waits and waits and waits until the lock becomes available. Sometimes this actually leads into what we call deadlocks, which is like nobody releasing the lock, and then one core always stays and the other core is also waiting for this. So if there is some form of a circular behavior, you're gonna have problems. But in most cases, what happens is that one of the cores already have the lock, and now this core is waiting for lock becomes 1. The moment that it becomes 1, it actually breaks from this loop, right? So it actually breaks from this loop and continue. It writes 1 to the lock, right? So it means that now I have grabbed it, and then it returns from this function. So at this point, this core has lock equal to 1. And now other cores who wants to grab this will see that lock is equal to 1, so they cannot grab it. They will busy wait in their while loop, right? So that would be the implementation. This would be the assembly version of the same thing. So if I have some form of a loop here, we can call this a lock loop or just a loop. What it does is the following. Let's say that the lock is actually stored in this address. It's stored in address 0x1. And then what we do is we are branch not equal to RA, and then continue doing the loop if this is not equal to if this is not equal to 0. Okay, so what it does is that it continue looping if the lock has not been acquired, right? But the moment that this returns 0, it means that I grab the lock. It means that the lock is available to be grabbed. So what I do is I essentially write 1 to RA, and I write RA to the lock memory address, right? So essentially all I do here is that I'm saying that lock is equal to 1, and then I continue my my instruction. Okay, so that would be kind of like what we are doing here. And as I said, we are assuming that the address of the lock is a memory address, which is the address is stored in X1. Okay, so that's kind of the assumption. Yeah.
It's like block.
You don't want the instruction. You mean here? You don't want the instruction be reordered? Yeah, so you don't have a problem with reordering, because again, so don't forget that you still have the out of order execution and ROBs and all those things. So things are actually like, so there is like, for example, a dependency between these two instructions, which means that the branch not equal 0 is not going to be executed before the load. So all of those things that we learned about draw data, hazards, and control flow dependency still applies here. So exact for this particular instruction, since all of these guys are dependent to each other, you're not going to have the reordering of an adult. So this works perfectly fine. Okay, and then how does the release work? Release is very simple. So release is essentially just calling the release function and writing 0 to the release, right? And then all you need to do, for example, is storing 0 to the address. So it would be kind of like, similar. In this case, it would be store word x0 0x1. That would be your release function. It's very simple, simple implementation, right? But is this gonna work? I mean, can you see a problem here? Anyone? Think about multi-core. Like, what happens if 2 cores tries to run this at the same time? What will happen? Yeah. So two cores. So think about like, the sequence that is happening here, right? So here and here. So what will happen is that let's say core number one is spinning on this loop, and core number two is also spinning on this loop. So the first two instructions are essentially the same, right? And now say and let's say core number three has the lock. So at some point, core number three will say, okay, lock is equal to 0. I no longer need it. Go and grab it. So both of these cores going to see this, right? So this one is going to think that the RA is no longer 0. So it's going to like move forward. But then core number two might also running the same grabbing. And if the time that we are writing happens after this branch not equal to 0 in core number two happens, then we're going to have a problem because both of them think that they have the core, they have the lock. So the example basically here is that if this instruction happens, and then this instruction happens. So this would be 1, 2, and 3. What will happen is that in next cycle, both of these cores think that the lock is available. So then this will happen. For example, this would be 4, this would be 5, but then it writes, but although it's even already 1, but what will happen is that it never checks back the lock, right? So it thinks that at this point, oh, I have the lock, I can continue. This one also thinks that it has the lock and it will continue, right? So you will have a situation where if this instruction happens after this instruction, then you are in trouble, right? Yes. Each core has its own set of registers, yes. But they are both reading it from the same memory address, right? So they're both reading it from, so this address and this address is exactly the same because lock is a global variable, right? So everybody has access to the same lock. Otherwise, if everyone has its own lock, then it's not a lock, right? Yeah.
So in that case, I'm checking status.
Yeah, you can assume that every time that we are doing a load, this is essentially an access to the memory, of course. Good. So we have this problem. So how do we fix this problem? Yeah. Exactly. So this is the notion of this is the notion of atomic instructions. Okay. So atomic instruction means that when you're running a sequence of instruction, this sequence of instruction happens in order. That is like reordering is not possible. But more importantly, it happens in one go. That is no interruption. In other words, you kind of like, as I told you, that there is this release consistency kind of situation. What this does is making sure that if I'm running this sequence of 4 instructions, this cannot happen in between. So I can only run this 4 and then I can run this 4. Okay? So this is the atomic operations. That is essentially the trick to fix this is that think about this as one instruction. So I kind of like define the whole thing as like, let's say I just making up an instruction called atomic lock. So it's one instruction. So either this instruction happens or this instruction happens. So this way I can, so both of these guys are trying to run one instruction atomic lock. Whoever does it first grabs the whole thing. The other one will not be able to grab the lock. Okay? So we kind of combine things in hardware doing that. And remember, long time ago, I said that, oh, in BRISC, we want to do one operation per instruction and all that. Here, now we want to have multiple operations per one instruction kind of situation. Okay? So that's what we want to achieve in particularly in this case. Is that clear? Any questions here? So this is called atomic operations, and almost all the main ISAs support atomic operations in a system. Okay. So how do we actually implement this? There are various ways. I'm going to actually show you an exact instruction in RISC-V of how we do it. At the software level, at the operating system level, there are primitives that are common to use. For example, there's this famous thing called swap, which what it does is an atomic swap, which kind of like, implement this way. There's other things called compare and swap, fetch and add. So these are kind of like more conventional names that you probably have heard about when we are like, taking courses in the operating system. But what they do ultimately is that particular operation, in this case, swapping operation, happens in one instruction. So what does swap means? In this case, swap means that means that if I do x and 1, it means that it takes the value of lock and writes it to x, and then it also writes 1 to lock. Okay? So that's what the swap means. That is basically in one go, it reads the value of lock and write 1 to it. If the lock is already 1, nothing happens. You cannot grab the lock, right? If the lock it was 0, it grabs it and then immediately write 1s to it. So it means that it is guaranteed that I'm now returning this value. So if you think about this is actually, by the way, called test and set. So you're testing the lock and you're also setting the lock in the same go. So what it does is that it returns this old value, okay? And this old value is the value that is receiving from this swap function. If it's 0, it means that I grabbed the lock successfully. If it's 1, it means that I didn't grab the lock. So I can put this test and set into a while loop, and then when I break that while loop, it's guaranteed that I grab the lock successfully. Okay, you got a question?
Yeah, so like my swap here, something fails, you got balance.
You don't backtrack. You just swap. So you read the value of lock and you write 1 to it. That's all you do.
No, but like atomic construction, something was to fail, then everything that happened after have to be reversed. Right? Like either everything is equal or
So that's a good question. The question is about how do we actually implement the atomic? There are 2 ways to implement an atomic. There is a transaction-based atomic. So there are this notion of transaction memories that allows you to just do one thing at a time. So read and write at the same time. Or there is this kind of a failure. So I'm going to actually show you how we implement it in RISC-V, and you see that both of them are options. So atomically, yes. So you read, but if someone else write to it, you fail and you redo. So that's a possibility.
One by one, like you have to make sure that but like you also have to, if it's a set of instructions that something with an atomic fun, that's an exception, right?
Yes.
And then you have to.
Yeah. I'm going to show you the exact implementation, and then you can ask this question again if you have. Yes.
Is that referring to just in order one right?
Yeah, in order. When it says in order, it means that these things happen in order, right? So like, the load word happens first, branch not equal to 0 happens next, and so on. And it's so from the perspective of the other core, these are uninterrupted, which means that either the whole things execute to its entirety, or it doesn't at all. So you cannot like run one instruction in the middle from the other core. So it's more of like, okay, core number 1 is executing, everybody else waits. Okay? Yeah.
But in order to get an instruction that has those 4 instructions stored within one other instruction, you have to use like one or a set of predefined assumptions instructions.
Yes. I'm going to actually show you the exact implementation in RISC-V, and you're going to see how we are doing it. So there are 2 ways of doing this in RISC-V. So I'll show it to you in a few slides. But as I said, this is one way, and then this test and set is kind of like traditional way of implementing this. So what it does is that you continuously test and you continuously set, right? So we read the log, you return the log value. If the log value was 0, you're successful. If the log value was keep reading 1, it means that someone else is already grabbing the log, you have no success. But the important thing is that the difference between this test and set and what I showed you before, and I said this does not work, is that this has this atomic swap thing. That is, when it reads the log, it immediately write 1 to it. So it's impossible that 2 cores do swap at the same time. One of them will be successful, the other one will not be successful. Okay, so that's the more important thing, that why this will work correctly. Yes. Yeah. Swap does the following. Swap reads log and put it in X and writes 1 to log. And this happens in, think about it as one cycle. It's not happening in one cycle, but think about it happening in one cycle. So instant. Okay. All right, so back to the questions that you guys had, that, okay, how exactly do we implement it in real world, in real ISA? So ISA, like RISC-V, I mean, different ISAs implement this differently. In RISC-V, we have these 2 key instructions called load reserved and store conditional, okay? Load reserved, usually shown by LR. In the past, I think it was also called load link, but usually we call it load reserved. And store conditional, okay? These are 2 specific instructions. These are actually assembly instructions, similar to load board or store word. You have LR and SC, okay? So what does LR and SC do? LR and SC is like regular load, but it also reserves that line in the cache or in the memory, that basically says that if between a load reserve and a store conditional, another load or store happens to the same address, then that store conditional will fail. Okay, it will return a number, a failure signal. Okay, so here's what happens. So in this case, I'm loading the address x1 to x2. So this is reading the log. Okay. Now I'm trying to add 1 to the log and write it back to the to the address. Okay. So what it does is that here it checks whether at this point someone else has read or write to this address. If they do, then this store conditional will fail, and this branch not 0 will not be not 0. So will basically, it's going to be not 0. So the failure will be 1. It means that I will jump back here. So I keep repeating this process, and then it's very similar to the swap function. So essentially it's read the value, write 1 to it, but it also checks if someone else is trying to read and write to it. If they do, this store and load fails. It means that, okay, I couldn't read the log properly, so let's redo. It only successful then if during this time period, there's multiple clocks, how many clocks this is, nobody else touches that line. Okay? So that's how we actually implement this in this things. So here's the kind of like, the full description. On load link, and as I said, load link and load reserve are the same thing. So so this is also equal to load reserve. So you will probably see the both. I think the actual official opcode for load link is LR. So you probably see this more often. So on the load reserve or load link, processor remembers the address. Okay. On the write, it checks if someone else tries to write. If a write detected, then the stored conditional will fail. If the write is not detected, then it works. Okay. And then usually this is implemented via the E state in the messy protocol. Remember, we had the exclusive, and we said that the exclusive will help you to understand whether this line is only loaded by you or loaded by others. So here's how we're going to actually basically do this. So when we are reading the lock, we make sure that everybody else invalidated and we go to E. Then when we are writing, when we want to move from E to M, we check whether we are still in E or are we in S or are we in I, because if someone else is trying to write. Only we move to M if we are still in E. If we are in S or I or any other states, that's a failure. So this is very simply implemented in a multi-core processor. All you need to make sure is that you continue to be in an E state. If you're in an E state, then you're good to go. Yes.
People do that. After loading the notification, there can be no load.
Yes.
If there's loaded between them,
Load or store.
what's the return value of store function if we have some other load store?
1.
Why?
Mhm.
So that will like reach the threshold zero, and we just like.
Yeah, loop back. Yeah, you check back. Yes. So you continue checking until you grab the lock. So again, this is similar to the while loop that we had in the past. You wait and wait and wait until you successfully read the lock. Yeah.
The lock while it's stored on the I.
Mhm.
Will fail.
Yeah, it will fail.
But then isn't it like other cores are trying to read the lock at all times? So how will this core ever end up actually getting the access?
So one of them will be succeeding, right? So one of them will eventually be able to read the lock properly. So all of them trying to read, right? So this one reads and successfully writes to it before the other one reads. So you usually like at least one of them become successful after a while.
Kind of like a chance for
There is a randomness aspect to it. As I said, there are a lot of works on like making sure that the fairness of this works in order also improving the performance. I'm gonna later show you that like keep reading the lock is not the greatest way of doing this because it's just unnecessary load and stores, right? And you're kind of bloating your memory bandwidth with this just unnecessary load and stores. So there are a lot of ways of doing this properly. Here, I'm not talking about the improving the performance of it, but you're in the right track. There are actually, we need to think about the better ways of doing this. But eventually it will work, but it's not the cleanest way of doing this. Mm-hmm. And then when I say messy, this could be also MOESI or it could be MOESIF, right? So here I'm just saying you need the E for this. And that's why I say E is really useful in many of these multi-core systems. Okay? Another alternative in RISC-V is this AMO instructions. So AMO is atomically read, modify, write the location at the address that it provides, okay? So there are actually these AMO instructions. There are a bunch of them. So there's the AMO swap, there's AMO add, there's AMO XOR. So all of what it does is essentially just read, modify, and store the value to that address in one go. It's one instruction, and it simplifies these things very nicely because essentially it's just one very clean instructions that you can use in RISC-V. So generally for load reserve, load link versus store conditional versus AMO, which one to use? You can use both. Load word is kind of like, read the values and fail and redo things, okay? Versus AMO is more of a transactional memory kind of situation that allows you to kind of block that address, do all of your operations, and then unblock that address and let others to do that. So it's kind of like, think about it this way. So for AMO, if there are two access to the load address X from different cores, so this one's core number 1, core number 2, if this is an AMO load, for example, an AMO something, what it does is that it serves this, but it blocks this. It doesn't even provide any response to it. So it's kind of buffer this request. Once this request is fully finished, then it serves this request. So the memory controller is able to kind of like decide which sequence of instructions to first execute and then second sequence of instructions. The difference though is that AMO is usually more complicated to implement in hardware, right? So that's why you have both options if you want. Okay, here's the assembly version of load reserve and store conditional, as well as the different types of AMO atomic rights operations. That could be a swap, could be an add, could be an XOR, could be an add, or, and so on and so forth. Okay. This will acquire and release. So these are 2 bits, 1 single bits. So these are flags. So they actually can support the serialization as well. So these instructions nicely give you 2 things. It also gives you the fact that this basically, if acquire, for example, is 1, it means that it should ensure that all the memory writes to the other cores are visible to this core before this instruction completes. Okay? So it's also serialized all the writes before. Remember I told you that release consistency means when we get the lock, we need to make sure all the other writes are finished. And when we are releasing the lock, we need to make sure that all of our writes are visible to others. So these 2 flag bits is actually giving you that. So if it's 0, it means that I don't care. I just want to grab my lock and that's it. But if either of them are 1, then you also need to enforce that in hardware. So RISC-V naturally supports the release consistency model inside their instructions as well. Okay? Any questions? Great. So for locks, we have the test and set, we have the atomic operation, we have the load reserve, store conditional, and we have the AMO operations in RISC-V. So these last one is particular to RISC-V instruction set architecture. Okay, and as I said, locks are commonly used for release consistency models. Typically, we combine these 2 things together. Okay. There are a bunch of optimization. Yeah.
But for AMOs, it's not that like all the buttons are still not being.
Yeah, so AMO, what it does, it guarantees you that this operation, this read, modify, write, happens in 1 instruction. That is, you cannot read and then some other cores do something in between. Okay? So all of these is read, modify, write. Okay? So all of these says that these things, think about them, happens in 1 cycle. Okay? So that's a hardware guarantee that is provided. Yes, it will support it by RISC-V processors. I mean, you have to check your processor to see if it's supported, because this is not part of the base. Not all the RISC-V processors supports this. You have to actually bake this into the hardware. But if your hardware supports this, then yeah, at the software level, you can just write AMO add like R1, R2, and then move on. Okay? Yeah, so the things that we learned at the beginning of the class was part of the base ISA, which means that all the processors that are based on RISC-V implementing those. But then there are a whole bunch of other extensions. So for example, you have a vector extension, you have a floating point extension, you have a consistent memory model or memory consistency extension. These are things that you would add on top of your processor. Not all the processors will have that. Of course, your processor, first of all, has to be multi-core to even need such a thing. If it's a single core, there's no need to have like an AMO because it's just a single thread all the time. Okay? All right, so some of the optimization, again, this course, we're not going to go through these optimizations. I'm just going to show you just one of them to give you an idea. But if you're more interested in consistency models, there's courses on parallel programming and all that you can do. So one of them that is like commonly used is actually converge on the conversation that we had, is instead of having something like test and set that we continuously read and write at the same time, we do this thing called test and set. Okay, so test and set is doing the following. It first reads the current value. If the current value is already 0, then it actually tries to grab it. If the value is already 1, it's not even going to try, because what's the point of grabbing the lock if the lock is already grabbed by some other core? Okay, so what it does is reading the value first. So this is a load and reads the lock. Okay, the idea here is that if the lock is indeed 0, then I'm going to go and try to grab it atomically. I might fail, so this is not guaranteed. This might fail, but at least I know that I don't issue an unnecessary store if the value is already equal to 1. Okay, so I'm saving a little bit of bandwidth by doing the test and set. So I first test, then do the test and set. Okay, so that's kind of like one, and then we put this test and set in some form of a while loop. Okay, so what it does is that it continues looping. It does the atomic operation, but it doesn't write until it at least thinks that it has the lock. Okay. Another thing that we do is we can use queues. So your question of like, okay, if there are multiple of these guys and all of them trying to grab the lock, and then this fails and this fails and this fails, and then all redo, and then again they fail, and then again they fail, and so on, what's the point? So what you can do is that you can in form of a queuing, right? So you can say that, okay, this one wants to grab the lock, this one wants to grab the lock, this one wants to grab the lock. I put them in some form of a queue and say that, okay, you can go and grab the lock, you can go and grab the lock, and so on and so forth. So I can actually maintain some furnaces like this. There's also like a lot of works on like what happens if I have multiple locks. So like there are different locks, different part of the code, all happens at the same time. How do I implement this? There's also additional challenges that I need to make sure. The problem with multiple locks is that it easily can lead into deadlock, because one core might wait for lock number 1, the other core might wait for lock number 2, the other core might wait for lock number 3, and none of them continue until they grab the lock, but none of them is releasing the lock because they're also waiting for the other lock, right? So you can easily get into this deadlock situation very, very easily and very, very quickly. That's why generally writing this parallel program is very, very hard. And you have to be very, very careful. Okay? So the bottom line is that there are a range of possibilities, but hardware provides some of these supports with like these instructions that I said, like a fence instruction, and or the store load, load reserve and store conditional, or AMU instructions. But the burden for parallel programming is mostly on the developer. So these are just tools for you. You have to use it properly in order to write your program. So ultimately, hardware is not going to fix the program for you. You have to just call these functions correctly to make sure that your program works. Okay? So that's all for the consistency and coherency issues. Any questions, final questions? Yes.
Okay.
So you're asking that if one core is grabbing the lock, what happens to the other core? Is that a question?
Yeah, and 2 cores gain the same lock. Like the second one that doesn't get a lock start executing other than waiting.
Yeah, so the question is about if I have 2 cores and both of them trying to grab the lock, and then one of them grabs the lock and continue, what happens to the other? Most of the time you just spin lock, so you're busy waiting. So that's why I'm saying, so you don't execute anything else, because typically there is nothing to be executed, because remember I told you that we want to have a release consistency. So you want to make sure that all the reads and writes here are observable by anyone. So if I start moving these things before this, then I'm going to run into issues. So that's why I'm saying that the performance of these locks are very important. It's also very important that your lock regions are small, because that means that the other things needs to wait. But typically, when you're writing these parallel programs, the lock part is really, really small. So majority of your time, you're just adding some partial sums and multiplying things. And only when you're like, writing the final value, you grab the lock and find it. So like 5% or less of your program is even in the lock. Yeah. Yeah. If the lock is in the cache. But again, even if the lock is in the cache, you need to have a coherency protocol, because these are the same address, right? So the lock is always the same address for all of them. You cannot like have your own lock locally stored and the other one has its own lock locally stored, because these two things needs to be the same thing. Otherwise, everybody thinks that they have the lock and then you're messed up. So it's still the coherency protocol and all that. And then usually what happens is that once the write goes to M, the other one goes to I. So it has to invalidate itself in the cache. Yeah. Schedule? Oh, doesn't try to get the lock at all? Yeah. So I mean, again, so the comment is about like, if I'm trying to get the lock and I don't grab it, and then do I like, forget about it and do something else? Is that's your question, right? Yeah, it could time out. And as I said, there are a whole bunch of things on the performance and the fairness that we are not getting into. It's not usually grabbed by hardware, it's the operating system level things that needs to be done. Yeah. But as I said, ultimately, you really need to write the proper code that does this. You also need to have proper debugging methods to understand why your code is slow. So many of these things, you write a parallel program, you expect that your system gets like 2x, 3x faster. But remember that like the meme that I showed you, that there was like one guy that's kind of shoveling and everybody else is kind of waiting. So that's the situation that most of the time happens, that there is one guy that's like grabbing everything. Everybody else is kind of waiting for that lock to be released and so on. So writing this parallel program is not an easy task. Okay, let's have a quick break. We're going to come back. I'm going to do like a more of a overview of things that we discussed in the class and some new topics. Okay? Okay. All right. So we are doing a full circle and we're going back to computer architecture systems. So you learn a lot of things, and now we kind of like wants to combine all of them together so that hopefully you have a system understanding of the whole thing. Just a reminder that there is a bonus question. If you didn't do it, do it. Closed course evaluation, I also posted on the campus wire. Please submit your course evaluation. I think the deadline is Saturday morning. So say it again. I don't think it's closed. I think it will close on Saturday. Usually it's closed on Saturday. But yeah, do those things, please.
Yes, Thursday, December 4th.
Oh, is it Thursday or somewhere?
It's 8 a.m.
Oh, okay. That's usually it's Saturday.
I know, it's a little weird. That's the email that I got.
Maybe it's a typo, because I think on the system I saw 6. But I'll double check. It is the 6th? Yeah, that's what I saw. But can you do it now or?
Now.
Yeah, but well, we'll clarify. All right. Okay, so as I said, this part is not going to be part of your quiz, just FYI. So this is just more for you understanding the whole thing. So a system as a whole, in a computer system, when you're dealing with like a big system, either it's like, a low-end embedded system, it's your laptop, it's a server, there are more things than just the computer, the CPU and the memory, which was the main kind of focus of this class so far. There are a lot of other things generally referred to as I/O or input and output. In fact, if you actually look into like system like a very complicated SoC, like a TI, there is like the cores are actually very small part of it, like the red part is mostly the cores. But then there's a whole bunch of other things that's going on. There is like different protocols for accessing the I/O. There's circuitry for clock and power and debug. There are a whole bunch of modules that you connect, like you have a Wi-Fi module, you have a Bluetooth module, you have the power module, you have your speaker and sound system, you might have your keyboard and mouse, and all of those other things. Okay, so you need to also be able to connect those and talk to them and read and write to them and so on and so forth. Okay, so this is kind of like go to the class of what we call IOs. Okay, and then IOs, depending on which device you are using, there might be different type of IOs that you're going to see. If this is a PC or a server or a mobile or an embedded or like a wearable device, the type of IOs that you see are different. Usually you have different type of storage, so you can have multiple secondary, ternary storage systems. You usually have network, right? So these days it's almost impossible to have a computer that is not connected to some form of an internet or at least some form of a Bluetooth or network. Then you have a bunch of different human machine interfaces like keyboard or mouse or touch screen or audio or video. Then you have some form of like a printers, but then most commonly again these days you have different types of sensors, your camera, your GPS, and so on. And then what we are shifting toward is world of actuators, right? So like we have the world of like physical AI, which is now all of your decision making in your systems now is applied to some form of an actuation. Like you have a robot, you have an autonomous car, all those things are into the category of actuators. Okay, so what would be the structure of such a system? The structure of such a system is usually like this. Okay, so you have a CPU that sits on top, and of course this is the most important thing in your system. This CPU could be multiple cores. Typically they sit into the same silicon chip, multiple of these. Then you will have your caches. Okay, so and again, caches could be private, could be part of the CPU chip. So some of the caches could be here, some of them could be into some form of an interconnect. Then you have your memory bus, and then you have your DRAM sitting there. Okay, and then you have your IO bus. Typically, we have a separate bus for memory and the IO. The reason for it is being that you want to have a dedicated lane between your memory and your CPU because that's the most important thing. But then you have your bus. The bus means that you can, first of all, you can have dedicated lines from each of these. So for example, if you have a really precious IO, you can directly connect it to the CPU. Okay, but you have the pin problem, right? The shoreline problem, usually call it that. The number of pins that you can have here is not unlimited, right? So these chips are like usually 10 millimeter by 10 millimeter. Each one of these pads are in order of like micrometers. So you have limited number of pads with each side of this chip. So you cannot like just grab any IO that you want and directly connect it to your CPU. That's why you want to use some form of a bus structure that you put your IOs, and these IOs are controlled by this bridge, and then this bridge is actually connected to your CPU. Okay. As I said, there are other options. So for example, you have crossbar architectures that everything is connected to everything else, or selectively are connected to each other. You can also have what we call network on chip or NOC architecture, which everybody is connected to some form of a router, and these routers are connected to each other. So that could be also another possibility of your system as well. Okay, so it doesn't matter which one you're using. In all cases, you need to support the structure. There are tons of research on the I/O, the technology of the I/O, the networking aspects of I/O, and so on and so forth. And again, these are the things that you've probably seen in other courses, in other classes as well. A big question is that, okay, if I want to read and write from the I/O, how do I do it from the processor? Let's say I want to read something from my keyboard. How does exactly this happens in let's say RISC-V ISA and in the program? There are two options that you use. Usually, there are, from many systems, there is a direct channel which is controlled by these things called CSR, or control status registers. Okay, these registers allow you to configure these different things. So, for example, say that, oh, okay, this has this many pins, it has this protocol, and so on and so forth, and then it reads and writes. So it buffers the data into the registers and then reads that register into the program. So if I have this CSR, most of the ISAs, including RISC-V ISA, you can treat this CSRs similar to your X1 and X2 and so on and so forth. So you can actually directly read and write to them the same way that you did read and write from your registers, okay? That's one way of doing things. So you can actually directly integrate this into your code. But this is unfortunately not very scalable, right? So you're not going to have many registers for different IOs. You usually have very limited registers for IOs. The more common way is what we call memory map IO, or MMIO. The memory map IO is that thinking about your IO as an extended version of your memory. Okay, so remember that I said that, oh, okay, this is your DRAM, these are your addresses. What you would do is that you say that, okay, any IO that I want to map, I basically map it as sequence of addresses inside my memory space. Okay, so for example, I say that address X to Y belongs to my keyboard or my Wi-Fi module and so on and so forth. So what that does mean is that essentially accessing to IOs is similar to accessing to doing the load and store. So you load and store, the address only changes, okay? And then you can do all those tricks that we discussed in the class about virtual addresses, physical addresses, address translation, caching, and all those things applies here as well. So all you need to do is essentially telling your system that I have this IO installed in this address range. So if you want to talk to your keyboard, here is the code for it, how to address it. That's why you usually have this thing called a driver. So driver is a set of libraries that you add to your program, you call them, you kind of set their address, so you usually have the operating system installing that driver, understanding that set of addresses, and so on and so forth. And then if you want to read to your keyboard or write from your keyboard and all those things, you essentially call those functions, and at the end of the day, at the lowest level of hardware, this becomes a load or this becomes a store. So you know how to deal with that. Same story happens here. There's a whole bunch of things that are happening at the OS level that you need to kind of like map the addresses. You need to check those things. You create a device tree and all that, which is separate from what we need to worry about here. Yes. Yeah. So the question is like, how was the timing happens? Yeah. So think about this as like a TLB miss that is like going all the way to the IO kind of thing. So it's usually very, very slow. That's why, for example, reading a key from your keyboard is in order of milliseconds. So you're not like actually reading a lot of things from your keyboard. Same thing with the other things. There are tricks to make this faster for specific IO. So for example, if you have like a high speed IO that requires you like read and write a lot, then you actually engineer this to make it very fast. Important thing about IO is that typically you don't also want to cache your IO. The reason for it is that IO is like a one-time thing and it's continuously changing, right? So for example, let's say you have a microphone that you read the values, right? There is no reuse of that sound, right? So usually you don't cache the addresses, but again, then nothing prevents you from caching the addresses as well. You can also, as I said, use the virtual addressing to address it and all those tricks. So all of that happens. You can also share them. You can have coherency, consistency issues. All of these things happens for the IO as well. Okay, so that's one thing. The second thing is the communication protocol. So there are many different protocols for when you have an IO that wants to communicate with your processor or from one IO to another IO. You probably have heard things such as IDE, PCI, SATA, Ethernet, PCIe. These are all different types of communication protocols for talking to and from a component. Okay, the older ones was IDE and PCIe. I don't know. Have you guys seen these IDE cables in your life, or anyone? You did? Good. Yeah. So there was like, back in the day, there was like this like very ugly cables that you connect to your motherboard, which was IDE. These days, most of the things are PCIe, right? And then now newer versions are CXL. These are just protocols. For example, the way that you probably have heard about like things like I2 squared or serial, right? So these are all different protocols that defines how do you send the data, how do you receive the data, how do you actually encode the data, what is the error correction, what is the signaling, what is the handshaking. There are a whole bunch of things that people define and standardize it. And then it's just important that both the CPU and the IO understand the same protocol. At the end of the day, that's the most important thing. The key challenge here is how fast and how much bandwidth you have to send and receive things. So the newer versions like PCIe, which is PCIe enhanced, is doing is that it allows you to have bigger bandwidth. Part of it is coming from the technology because we managed to shrink the size of these wires and improve the energy efficiency of it. Part of it is also because we managed to clock them much faster. And part of it is also the protocol itself has been innovation in the protocol. But bottom line is that there are a whole bunch of these protocols. If you're interested, definitely if you start working on firmware or system integrators in these companies, many of you might actually work on this all the time in your life. So there are actually lots of challenges of signaling and crosstalking and all those things that goes a little bit lower than computer architecture, but still has something to do with computer architecture. There's another very important component in most of these modern systems called DMA. DMA stands for direct memory addressing. So the idea is the following, is that if I have my CPU and then I have a bus, then I have, let's say, an IO. The way currently it works is that I said that essentially any read and write from the IO is reducing to some form of a load and store, okay? But now imagine that, for example, you have a camera and you want to stream, you want to record, for example, a video. So what you want to do is that you want to have a channel between your IO and your memory, right? And if I don't have a dedicated channel that can do this, what will happen is that I basically do this very inefficient thing that I read and write things from the CPU, and then from the CPU, I read write things to the memory, okay? And this is not very efficient things because one, CPU is being involved in something that it has nothing to do with. And then second is there is this round trip that is your pain. So what usually we do is that we're introducing this additional component called direct memory access. That what it does is that first you will configure this DMA from the CPU side, but then what it does is that you're basically saying this DMA that, okay, you want to store this many bytes in the memory, here's the address range for you to go and write. So DMA can essentially issue its own read and writes to the memory without CPU being involved, okay? And this is great for streaming. For inputting and outputting data, this is how we usually implement things this way, okay? So we're gonna have DMAs on the bridge. We're gonna have DMAs, for example, on GPU. We're gonna have DMAs on all of these other systems. And this will allow us to directly talk to and from the memory. For For example, the network card usually talk to the memory all the time, okay? So as I said, this basically offloads the work required by the CPU in the DMA. And once the DMA is finished, it's usually, raise an interrupt, allowing and letting the processor know that, okay, I'm done with writing or reading, and then you can move forward. Of course, the security of this is also very important because you don't want to also allow any IO to write anything arbitrary to the memory. So that's why usually the initiation processor has to be authenticated and done by the processor. But once you initiate that, you make sure that you can only write to those addresses and move on, okay? And this would be essentially a bigger picture of a more modern processor. So usually a modern processor, as I said, has a CPU, has a DRAM. Typically, all these current systems also have a GPU that is also connected into its own bus to the system. Graphic can also usually directly talk to the DRAM as well. Then you have your I/O bus bridge. So you can have a device here, another device that has DMA. Not all the devices require to have DMAs. Then you can also, as I said, have different tiers of I/O. So for example, you can have a PCIe, then you can also have a PCI, and many others. So you might have multiple bridges on the same bridge. So you can have bunch of IOs here, another bus, and bunch of IOs here. So you can have actually a hierarchy of buses if you want to. As long as the CPU knows where each of these guys are and the range of the addresses, nothing prevents you from doing this. So if you look into, for example, the data sheet of from your motherboard, you will see that it says that, oh, I support this many channels for PCIe, I support this many channels for PCI, here's where the address range is. You can actually grab and extract all of these informations from the public products that you have and use in your systems, okay? As I said, buses is only one way of having systems. In many large-scale systems, buses is not the most efficient way. Why? Because if these two guys wants to talk to the CPU, you have to do some form of an arbitration, right? So you have to say, oh, IO number one, you talk for let's say 100 milliseconds. IO number two, you stand and don't do anything. Wait. Then you do the arbitration the other way around. Say, okay, now one wait, two talk, right? So this would be slow for the IOs that needs to be fast. So what we can do is we can do some form of a network. So the same way that we do network on the internet. So we can have the packet structure, we can send things over, we can receive and send things. This is also very scalable. So if I have a big systems of many GPUs and many CPUs and many memories and many IOs, I can actually create, all I need to do is essentially extend this into different directions, right? So I add more routers, and each router needs to connect to each of these components, a core or a memory or an encoder or an SRAM and so on and so forth. How does each router look like? So the routers are usually just sequence of bunch of buffers, okay, that receive it from different directions. Typically, they receive it from left and right and up and down, like a left, west, east, north, and south. And then they have some form of a connectivity. So typically, they have some form of a crossbar connectivity that, for example, if this guy wants to send something down, it can do that, for example, with this connection and so on and so forth. Again, we're not gonna spend a lot of time on this as well, right? But just wanted to say that designing the NOC correctly is a very important problem, especially now with the large-scale AI systems. This problem was like an old problem like 10, 15 years ago. Now all of a sudden becomes again a very important problem because now I want to have 8 GPUs or 100 GPUs connected to each other. So they need to be able to talk fast, and this is how you enable that. Okay. So there are many challenges in designing a large network like this: the performance optimization, scalability, energy efficiency, security, and so on and so forth. There are many design ingredients as well, like which topology are you using, protocol, routing logic, the router itself, and so on and so forth. So NOC, as I said, for itself is a very, very interesting topic. Okay? Any questions so far? All right. So I'm just giving you some of the important topics that you should know. Another very important thing is that, okay, I have network structure, either it's a crossbar, it's an IO with a bus, whatever it is. How do I actually interact with the processor? How do I notify the processor that I have some data? Is it always like, always I'm connecting, sometimes I'm connecting, and so on? So that goes back to the traditional things that you probably have seen in your life many times, the interrupt versus pulling. Okay, so the same thing happens for the IOs. The good thing about interrupt is that it has no overhead to the system, but it can happen and can disrupt other activities in the system. So if you are a non-maskable interrupt, then if you're running some program and then you have to jump and then service that interrupt, it will disrupt the system. Versus polling is the other way around. So it's always some additional overhead to the CPU. But the nice thing is that you can schedule it whenever you want to schedule it. Okay? And then usually you do some form of a hybrid approach where you initially do the interrupt and then switch back to the polling. For example, let's say you're planning to receive some big packets from your network card. So initially you don't check it. When the network has a packet that will, cause an interrupt, then afterwards you just say that, okay, I'm going to check your buffer every 100 millisecond or 1 microsecond or whatever. So that would be a polling based approach. And then when I'm done, I'm going to go switch back to the interrupt. So usually most of the systems doing this in this fashion. Okay. But how do we exactly execute this interrupt or trap in a processor? Like, remember I had like the PC and sequence of instructions. So where does that interrupt play in the system? So I have a program and I told you that I do PC plus 4 or like PC plus target and all that. So how exactly actually am I forcing the system to execute an interrupt? Execution of interrupt. So first of all, there are other things that they also usually use in modern systems called exception and traps. Exception is usually referred to when there is an unusual condition happening. So for example, dividing by 0 or something that you don't know. Trap is actually a synchronous event to handle the control to some other things. So trapping is something that is planned for, and we use it from either the operating system level or the IO level to execute things and change the programs. And an interrupt is actually refers to some external events that asynchronously tries to affect your execution. Okay? So how do we actually execute an interrupt is when an interrupt happens, there's usually a queue, right? That you buffer these requests. There's usually a sequence of priority, right? So you say that, okay, this interrupt has higher priority than this interrupt. You can also mask some of these interrupts and say that, okay, for now, don't care about these interrupts, but there's also some of them that are non-maskable. But eventually, when an interrupt happens and the CPU decides that it needs to service that interrupt, it calls an exception into the execution, okay? And when an exception happens, then that's when we execute a trap, okay? So how does the trap happen? So by the way, exceptions are things that you have seen before. So for example, branch misprediction is an exception, okay? So you have the recovery process, a flag becomes 1, and then you go and, I don't know, copy your register file back, you can change your PC and all that. So these are all exceptions. You have already seen exceptions in the design. Interrupt will also cause an exception. So essentially a flag becomes 1, you kind of stop the regular kind of like execution of your pipeline, and then you start following the whatever you have baked into the hardware of that exception. So for example, for interrupt, that means that I have to jump to this thing called interrupt vector table. So essentially I change my PC to point to the beginning of the interrupt vector table. Then usually, depending on the interrupt, there is an offset. So for example, if this interrupt is coming from a GPIO pin versus if this interrupt is coming from the network pin and so on and so forth, there will be an offset. This is usually an interrupt number. Within that offset, there is a function pointer that points to a specific PC address, okay? So the PC will become, like basically PC becomes the pointer, okay? And the rest of it is that we just execute normally from the pointer. So it's like calling a function, okay? So an interrupt exception is calling a function, but that function is decided by the interrupt vector table and the offset that you have in your system. You jump there. Once you're done with that function, which is servicing that interrupt, for example, reading some packets and all that, then you return, and the return is essentially go back to wherever the PC was initially. Okay? So the sequence of interrupt is you're jumping to the vector table, you're jumping from vector table to the interrupt handler, and then you jump back. Sometimes you might have nested interrupt. So while you're handling an interrupt, another interrupt happens. So you again follow this protocol. You jump to the vector table, you do the pointer, you handle the second interrupt, go back, handle the first interrupt, then go back to your original execution. Okay? So that's usually what we do in an exception. Important things about the exception is when we are jumping around and running these things, we need to maintain our states, right? So we have our ROB, we have our reservation station, we have our register file. When we are jumping back and forth, we need to be able to go back to what we were before, right? So if, for example, the interrupt changed some registers, do we need to actually recover those numbers or not? These are important. So depending on what we want to recover, you have either what we call a precise exception, which means that I'm able to recover everything exactly the way it was before, or I have a non-precise exception, which is like, I don't care. Maybe I can allow the things to be also changed. So I don't necessarily need to be worried about some of the exceptions. So for example, for branch misprediction, we need to have a precise exception, right? You need to go exactly to the way before at the point that the misprediction happens, okay? And again, IO events then becomes an interrupt. So essentially what happens is that we execute a trap, which is that sequence of instruction that I said. We jump to the vector table, we jump to the handler, we execute that trap, we get the value that we want, and then we come back and continue our execution, okay? You probably have heard about system calls, like, when the operating system takes over, operating system calls also implemented exactly as a trap. That is, you're running your program, the operating system wants to intervene and run something else. So what it does is basically causing the PC to jump to the operating system call table, okay? So usually system call also has some identifier and some table to decide that, okay, now I need to call this function. So again, your PC is continuing normally for running an application. A trap happens. You change your PC to whatever that trap is pointing at. You continue executing that. You jump back, you continue your execution. So that's how the operating system, the IOs, and your regular applications interact with each other with the settings that you have learned so far in the sequence of PC. Any questions here? There's a whole bunch of other examples. For example, what will happen if you have a hardware failure? What happens if you have an instruction, unknown instruction? What will happen when you have an overflow? All of these things will be executed as some form of an exception. So the processor has a kind of a list, these addresses, these instructions. They will start executing those and do some form of a recovery. So sometimes this recovery means that, oh, this is a big failure. I need to go back and restart the whole system. So I change the PC to the beginning of my boot, and I reboot everything and start executing from scratch, right? So sometimes that might happen. So that's why when your system quote unquote crashes, but sometimes you can also recover it nicely. So you can actually do other things. Yeah.
Modules, has a communication system, and like one bit is off, just because that can happen. Like,
Yeah.
is that something that would?
Yeah, one bit can be off as well. Usually we have error corrections to fix that, but if the error is detected but we cannot fix it, either we dump that packet and redo it. That's usually what happens. But yeah, if something happens along the way, you might actually, again, crash and restart the whole system. So this would be how your system would look like. Okay. So as I said, you have a bunch of other things, different cores, different components, the interconnect. So this is actually from an ARM core. So hopefully you kind of now relatively understand how these different things work. So you usually do memory map IO. We have DMAs. We have methods for executing interrupts. We have methods for handling traps and exceptions. And we have methods for reading and writing to the IO. So this way, combined with all the things that we learned so far, hopefully makes the whole, the big picture kind of makes sense for you now, that how the whole entire systems of many different configurations and many different modules works. Any questions? Great. So where are we? To kind of like, we started with this graph. Let's finish with this graph. So we are here. We are kind of flat. Things are not happening, right? So things are not getting much faster. But if you remember, I told you that this is actually not the end of things. And what happened was the AI kind of revolution happened. And many years we design our CPUs and our memories and try to run like multi-threading and so on. And then we made progress. But then we realized that, the traditional way of doing things is no longer good enough, right? Because we need fundamentally different ways of running things, especially for some specific kernels like matrix multiplication. So what we did at this point was, actually this happens like a little bit before, so somewhere here, that we start adding these other components to the systems, including the graphic processing units, GPUs, and neural accelerators. So you probably have heard about TPUs. So we introduced this thing called XPUs, like that's the term usually people use it. So NPU, TPU, GPU. So these processing units that are being added to the system. I wish that we had more time so we could actually go over it. I was originally planning to have a full lecture for it, but since we lagging behind and there were multiple lectures that was canceled due to the holidays, we don't have time to go over it. I'm going to just very quickly just give you very high level overview. The good news is that we have a course on GPU marker architectures at the grad level taught by another professor here. So if you're interested in GPUs, I definitely recommend you to consider taking that course. Okay? So is this the end? No. So there are actually in multiple directions that we are making progress. The three things that we are making progress of is called more, called more than more, and then beyond CMOS. So what is more? More means that those people are saying that Moore's law is actually slowing down. They are not right. So they're saying, many companies are still saying that, we can continue scaling. We can go to like 10A and then maybe smaller and smaller. And in fact, we are having 3 nanometers. There is like 10A, which is like less than 1 nanometer. There's like, another step. So there are lots of research on materials, on device fabrication, that is trying to drive that side of things. And this is very low level, kind of device level, physics level. There's also 3D stacking and all that helps you with that. And then the more thing also applies to the GPU and neural processor. So by adding these customized accelerators, we also managed to make things faster. And then at the system level, we also having tiers of the computer. So we have IoT devices, we have embedded devices. So we are actually managed to scale the system. We don't need to necessarily put all the features in all of our computers, right? Then there is more than more, which means that don't think about systems as just a monolithic single core, but think about it as 2.5D or even 3D architectures. So the latest and greatest systems now are not like one chip and that's it, but it's like one chip and then on top of it another chip and then on top of it another chip. So you can actually like it's like a multi-core 3D kind of situation. This has been commercialized for memories, so you can see it is actually for like called high bandwidth memories. For CPU and memory hasn't happened yet, mainly due to the structural failures and the temperature. But it's actually something that is going to happen soon. Yes.
How is that different from horizontal scaling or
Horizontal scaling with cores you can do, but then horizontal scaling with cores, that means that you put things in the PCB, and then the communication between them becomes very slow. So at some point, if they are far away from each other, there's no point of doing this. 3D means that essentially I put it in via what they call true silicon vias or TSVs. So they're incredibly fast. So you can actually talk to each other from different layers very, very quickly.
so like we ensure this can memory virtually speaking, how is like each layer structured?
So each layer would be like, I put a CPU here, and instead of putting my memory here, I put my memory on top of it. And then these things are connected via silicon. So there's like literally pillars, silicon pillars that going through their silicon from here to here.
So is it simply faster because physical proximity?
Yeah, from the physical and the technology. So when you have a PCB, okay, so if I have a CPU here and the memory here, I have this thing called bump. Okay, so like you probably solder, you've seen this bump. So these are like really like nasty bumps. But in like a commercials, there are like SMDs, so small bumps. But nonetheless, these are like few micrometers bumps. Okay, and they have a large capacitance. So from talking from this bump to inside transistors here, it's a lot of capacitance that I need to. So the delays are large. Okay, versus if I do it this way, it's no longer a bump. This is a TSV structure. It's just fundamentally physically different. So I can actually talk very fast. Think about it as like in your home, you go up the stairs versus you have to go to your neighbor's home and then go upstairs. So you have to come outside your house, go to the street, go to the next, like cross the street, talk to the other guy. So that's exactly same concept. Yeah. Semantically, from the architecture perspective, is no difference. Yeah. All right. So there's a whole bunch of these things called near memory, in-memory computation, near memory computation, 3D computation, chiplet-based systems that I personally work a lot on these days. So these are all in this category, and almost all the like state-of-the-art, latest and greatest systems, including NVIDIA GPUs, Intel processors, AMD processors, are all like this. So again, you rewatch the kind of keynotes this time, then when you're talking about this, you will see that they're talking about some form of these integrations like that. Okay? Then, of course, there's a whole bunch of things beyond CMOS. So far, we just limit ourselves to CMOS architectures, but there's quantum computing, neuromorphic computing, optical computing. These are like more far ahead, so we still haven't managed to build that. But the idea is that if we can make a quantum computer work, then many of the challenges that we are facing now with the von Neumann architectures will be solved. Again, not all the different benchmarks will benefit from quantum computing, but there are a class of problems that significantly will benefit from quantum computing. Yes?
Physically speaking, like quantum processor, are they made of silicon or what?
No, so they're not made of. They have a controller made of silicon quantum computers, but the physical devices are fundamentally different. They usually works at like lowest, like close to 0 Kelvin and all that. So you have to be like really cool.
It's like what's in the field?
Oh, the materials are different. Usually, like they call it 3.5, so like germanium. There might be silicon as well. So there's like, but it's fundamentally different than CMOS. There's no transistor per se. There's quantum gates. All right. So as I said, we unfortunately don't have time to talk about GPU. But essentially, I'm just in one sentence, if I want to talk about what is GPU and how it's different, is that GPU essentially is the same pipeline architecture as a CPU, okay? But what it does is that essentially does it the following. So that in GPU, your system is one giant functional unit. Okay, so your controller, your decoder, and your renaming and your reservation station, they're still there to some extent, but they are very, very small. Because what we do is this thing called single instruction multiple data. So in our CPU, we do one instruction with like RS1 and RS2, another instruction RS1, RS2. So that's why we need to have like a long list of, okay, this instruction is ready, now that instruction is ready, and so on. But in GPU, what we do is that we say that, okay, we want to add, there's one add, but instead of 2 registers, I have 1,000 registers. Okay, so I do RS1, RS2, RS prime 1, RS prime 2, RS double prime 1, RS double prime 2, and so on and so forth. So I have a huge size of register file, all of them doing the same thing, which is adding, but then I'm doing it all at the same time. So if I just want to kind of like show you that if this is your CPU and you have like 4 functional units, that would be your GPU. So there are many, many functional units. There is still RAM and control and cache and all that, but they are significantly smaller. Okay? So that's the fundamental difference between the GPUs and CPUs. Okay? And I'm not gonna have time to go over it, but feel free to look at the slides. So as I said, the branch prediction, the decoding is much smaller. The criteria for selection is much smaller. But on the other hand, you have larger ALUs, you have larger register file, and you need a lot of memory because you need to bring things in and out of the GPU much more. Okay? But they have ISAs, they have data pattern controller, they have fetch decode schedule, they have register file, they have FUs. So many of the things are similar. In fact, if you actually like look at the architecture of these things, you will see that you understand almost everything of it, unless a few minor things that is unique to the GPUs. Okay? This is actually like, the structure of within a core. So you see that there is a dispatch, there is an operand collector, units, result queues, and so on and so forth. But as you can see, there is many, many cores. So that's a fundamental difference. So usually we are talking about thousands of cores within one GPU. Okay? And then we run it. There's a whole bunch of other problems. And again, we don't have time for it. But take a look at this if you want. The biggest problem is what this called branch divergence. Since you have a single instruction, multiple data, not all the data will be available. So you will have a utilization problem in GPUs that you need to fix. And again, take a look at it. And there are many challenges in GPUs. Again, GPUs is the hot topic in computer architecture. So if you're interested, take a look at it. Beyond GPUs, there's also lots and lots of research on what is the next GPU. Like, if I want to be the next NVIDIA, what would that look like, right? So there's actually tons of these, startup companies that are trying to be the next GPUs. Of course, there are already examples of this, like TPUs. And again, since we don't have time, we're not going to go through them. The biggest difference between these specialized architectures is that they no longer followed by the von Neumann and instruction. They're followed by data flow architectures, which means that I baked in my instructions, sequence of instructions inside the hardware. I just flow the different data. Okay. So for example, this would be my system. I can only do this. I cannot do anything else. Okay. I can only do A plus B, B times 2, V minus W, and so on and so forth. So there's actually a data flow for this. What you can do though is that you can feed your data. You can change your data to this, and I can execute it for you. Why this is useful? Again, This is useful when you have something like matrix multiplication. If all I care about is matrix multiplication, or all I care about is neural network, I will hardcode my neural network here, and I just execute that. And that gives me huge amount of performance because I no longer need to be worried about my branch prediction. I no longer need to stall my processor for waiting the data and so on and so forth. So I can actually like maximize my design into something that is like literally designed to just do one thing, but one thing very, very fast. Okay, that's how we manage to make these things very fast. Okay, and again, take a look at these things. We don't have time for it. This is the structure of the TPU, and again, if you're interested, take a look at it. And that's pretty much it for the more than more. There's also security, but we don't have time for it. Just take a look at it. I put the slides in case that you're interested. The bottom line for security is that these things that we share, like the cache and the branch predictor and multi-threading and all that, the assumption is that we maintain the isolation. Okay, that is, one core cannot read things from the other core. Reality, this does not work. So the attackers can use this thing called side channel information that reads the access patterns of your cache in order to understand what exactly you're doing. So there's a whole bunch of research on security for architectures that how do I maintain my isolation without sacrificing the performance. So that's kind of like the very, very important challenge. And that's what my research is actually. All right. So I want to finish this maybe 2 more minutes and then I'll let you guys go. I want to just very quickly talk about things that we covered and things I want you to remember from this course. So we talked about ISA, we talked about marker architecture, then we talked about things like pipelining, speculation, parallelism. That was the majority of topic that we talked about. Then we talked about memory hierarchy, caches, main memory, virtual addresses. And then we shift toward multi-core designs. We talked about coherency and consistency. We talked about the system on chip today. And that was kind of like the topics that we covered in this class. The main ideas that we covered is we use abstraction. That was the first thing that I described to you. The second thing was that all of our designs were based on this very important principle that we make the common case fast. We make the branch prediction, speculative execution, all those things. And we said that as long as most of the time we are correct, we're going to get performance benefits, right? We do parallelism a lot. We do pipelining a lot. We do speculation and prediction a lot. And then we use hierarchy. So using the concept of hierarchy was one of the important things that we use in this class. So hopefully now you understand this picture that I showed you the first time in the class. And lastly, this is one thing that I usually do in my class, and that is, years from now, what should you remember from this class? Of course, you're going to remember all the things for next week, but you're not going to remember many things years from now. So here's your cheat sheet if you want to kind of like have this, that, okay, if I want to know about computer architecture, what really do I need to know? You don't need to know like MoEZF and all those things. We do those things just to give you a little bit of like puzzle and kind of like keep you sharp and have you, pay attention to the details. Conceptually, why though, as a computer scientist and computer engineers, here's the things that you need to know. You need to know what is an ISA and why we need it, and what is a micro architecture. What are the general design things that we consider? Okay, so remember that. Remember that we had some form of a controller data path and what was the role of each one. Remember that we had things like pipelining and why pipelining helps. You don't need to remember hazard and forwarding and which cycles did we do the forwarding and all that. You're gonna remember it. You're gonna forget it on Friday of next week. So that's not gonna be a problem. You do remember what was out of order execution in general, like what was the motivation, what was the challenges. Remember the concept of speculation and prediction, and know that many decisions in modern systems are based on speculation. Understand generally what cache was. You're not going to remember PLRU or LRU. You're not going to remember, write buffers or early wake up and things like that. But generally understand why we have virtual memory, how do we translate address, what is the cache and why is important. And finally, remember what it takes to run a parallel code, what is the role of the hardware and what is the role of the software for it. Okay? And then understand the overall system architecture. Understand what is a trade-off. Understand why we speculate and what are the trade-offs for speculation. Understand the trade-offs between power and performance and area. You cannot just, there's no silver bullet for any of these things. There's always some form of a trade-off that you need to take care of when you're designing these things. And that's it. That's all we care about. There are a bunch of things that we didn't talk about. This is a very useful lecture to watch. This is the authors of your paper, your book actually recently won a Turing Award, which was the highest honor as a computer scientist, except you're working on machine learning and you can win the Nobel Prize. But watch this video. This is actually very interesting video if you have time. You can also, if you miss me, you can follow me on social media. And don't forget your evaluation. See you next week. And that's it. Thank you, guys. Yeah.